Welcome back. Problem 111-14. So statement is the brick wall exert a uniform distributed load of 1.20 kips per feet on the beam if allowable bending stress is 22 ksi and allowable shearing stress is 12 ksi. So select the lightest wide flange section with shortest depth from Appendix B that will satisfy this and support the load. If there are several choices or equal weight, choose the one with the shortest height. So you can see this is the beam clear, and this wall exert a uniformly distributed load of 1.20 kips per feet. So select this wide flange beam with the shortest depth. So first step in solving this problem is to find the reaction force if we remove the support at this point. Let this is point A. So if you remove this, or so this will be, let this is point A and this is your point B. And if you remove the support at point B, so definitely there will be a reaction force at point B. And also this uniformly distributed load will be converted into point load. So for that we have to multiply this 1.20 into the length over which it acts. So it will be converted into point load and it will be acting at the half of this length, which is 5 feet. So I will also write that. So this is the load there, and this is 1.20 into perpendicular distance, into length is 10 feet. So this is 12 kips, and that will be acting at half. So this will be 5 feet, and remaining will be also 5 feet. So we will find this reaction force at point B and A. For that we will apply equilibrium condition that sum of all movement about point A is equal to 0, and taking the counterclockwise movement as positive. So about point A, one force is this one and perpendicular distance is this one. It is producing counterclockwise movement, so it will be positive, and this length is 20 feet. You can add them, so it will be 20 feet. So I will write RB into perpendicular distance is 20. The second moment which is produced by this point load, and this point load is 12 kips and perpendicular distance is this 9, because 5 feet plus 4 feet will be 9 feet, and it is producing clockwise movement, so it will be negative. So minus 12 into 9 is equal to 0. Okay. So from here you will get 20 RB is equal to 38. 12 nines are 108. Not. So from here you will get RB is equal to 5.40 kips. Okay. We will now find RA by using this equilibrium condition that sum of all forces along y direction must be equal to 0. So you can see we have three forces. One is RA, other is RB, and third one is this 12 kips that is acting downward. Their sum must be equal to 0. So RA plus RB is 5.40 minus this 12 kips is equal to 0. So it means that RA is equal to 12 minus 5.40, 12 minus 5.40. So RA is equal to 6.60 kips. Now you have both the reaction forces, so you can draw the shear force and bending moment diagram. So I will also represent over here. We have RA is 6.60 kips. Similarly, we have RB is equal to 5.40 kips. And we will draw the shear force and bending moment diagram. Okay, so what we will do, I will draw horizontal vertical lines from the end. Similarly, from here I will draw vertical lines. And first step is to draw the shear force diagram. So this will be the length. This will define the length. X is length. So shear force will be in kips. Now you can see at this point we have a shear force of 6.60. So if each division is of 2 kips, so 2, 4, 6, and this is 8. So 6.6 will lie somewhere here. Clear? Now this till this is 4 feet length. This is 10, sorry. This will be 10 feet and this remaining is 6 feet. This is 6 feet. This is 10 feet and this is 4 feet. Now you can see from this diagram that this 6.60 will remain the same till 4 feet. So this is 6.60. Now here we have a uniformly distributed load. So if you multiply this 1.20 with this 10, so it will be 120, 12. So 6 and this 12 will be minus 12 because it is downward. So at this point we have, from this point till this point we have minus 12. So 6.60 minus 12 will give you minus 5.40. So this is 2, this is 6. So 5.40 will be somewhat here. And you can see that this load is a straight line with 0 degree. So shear force will be 1 degree higher and that is downward. So if we join these 2 points directly, I will draw a straight line. So you have to join them using a straight line. So this will be your load, and this will be at this point we have 5.40. Now from this region to this region you can see there is no load, so this will remain same, and at this point you can see plus 5.40. So minus 5.40 plus 5.40 will bring it to the 0. So this will be your shear force diagram. Now with the help of this shear force diagram, I will draw the bending moment diagram. So for bending moment diagram, I will draw a horizontal line to represent the length of beams. This is moment that will be into kips into feet. Now you can see that our first, if you take this region, so this is the area under this shear force will give you bending moment, and this height is 6.60 multiplied by this length 4 feet, which will give you 26.4 if you multiply both. Clear? And since this line is horizontal, so the shear bending moment will be the first degree line. So 6.60 multiplied by 4 will give you 26.4. So let each division is of 25. Clear? Or you can say if each division is 10, 20, 30, 40. So this is 40 kips into feet. This will be 30, this is 20, this is 10. So 26.6. So 26.6 will lie somewhere here. So our first point bending moment will be this point. This is 26.4. Now we will move toward the second region, that is this one, and this is a triangle, right angle triangle. So its area will be equal to half of its base, which is 10 divided. Okay, so we do not know what is this length. So if you have proper design it or proper calculated it. So this will be, this distance will be, you can check this distance will be 5.5 feet. Okay, you can also calculate it by putting the x is equal to 0 in shear force. For that you will need shear force diagram. I'm going to write it directly. This is 5.5. so now this area is half of 6.60 multiplied by 5.5 will give you 18.15. So 18.15 plus this 26.4 will give you 44.55. So at this point you have to plot 44 point at this point at 44.5. So 44.5 will be somewhere here. This will be 44.55 kips into meter. Now you can see that this shear force line is a first degree line and slope is decreasing. So bending moment will be a second degree curve and that will be clockwise. So I will draw this like curve. Clear? Now the another area is this one. Clear? And this remaining distance is 4.5. So this area will be equal to half of base, which is 4.5 multiplied by this height, which is minus 5.40, will give you the value when we'll add it with 44.55 will give you 32.4. So 32.4 will be somewhere here. This will be 32.4. I will repeat, when you take this area, which is 1 over 2 into minus 5.40 multiplied by 4.5 will give you a minus value, which when added with 44.55 will give you 32.4. Also the slope of this line is decreasing and it is first degree line. Clear? So bending moment will be second degree and it will be also curved and that will be clockwise. It will not be a straight line, but that will be in curve form. Okay, now we have only left with this area. So this area is 6 feet multiplied by this height, which is 5.40 minus multiplied by 6, which will give you minus 32.4. So plus 32.4 and minus 32.4 will bring it to 0. So I will straight join it because you can see this is a line with a 0 degree. So this will be your bending moment. Now from this bending moment diagram, you can calculate the maximum bending moment. I will choose another color. So maximum bending moment is equal to 44.55. You can see this is the maximum value, that is kips into feet. Okay, now we know that section modulus, minimum section modulus required section modulus is equal to maximum bending moment divided by allowable bending stress. So maximum bending moment is 44.55 kips into, I will convert it into inch, so it will be kips into inch, divided by allowable stress, that is given as 22 ksi. So 22, and you will get required section modulus comes out to be 24.3 inch cubic inch. Now with the help of this required section modulus, you will go to the appendix B at the end of this book. So we'll move toward book and we will check the required or alternate or required beams, wide flange beam. So Appendix B, you can see where Appendix B. So this is Appendix B, that is about wide flange section. So this S is equal to 24.3. So you can check this S values over here. So if someone matches, so we will go searching for 24.3. So 24.3 is 1422. You can see one is 29, that is near to 24.3. Our value was 24.3 and one, this value is 29 greater, so we will accept this one. And if you move further, so from here you can see one is this one, which is our required value was 24.3. Now you can choose either W12 by 22 or W12 14 by 22. So we will check which has the both section modulus are greater than the required, which is 24.3, but we will check the shortest depth. So which one has the shortest depth? We will check that. You can see the second column is about depth. So if you check the depth, it has 13.74 and the other one has 12.31. So this has the shortest depth. So we will choose this one. Also, I will write down some values of this wide flange beam, its depth. Note down this thickness of web, which is 2.60, and SX, section modulus 25.4. So we have chosen W12 by 22. So based on section modulus I have explained, we have selected W12 by 22, and some of the property of W12 by 22 section modulus was 25.4 cubic inch. Its height was 12.31 inch and its thickness of web was 0.260 inch. Now we will check whether we have selected a correct beam that will satisfy our condition. So also we have allowable shearing stress was given as 12 ksi. So we will check that. We know that maximum shearing stress is equal to V max divided by I height of this beam into thickness of web. So V max from this diagram can be seen that it is 6.60, the maximum value. So 6.60 divided by height is 12.31 into thickness of web is 0.260 inch. So when you calculate it, you will get tau max comes out to be 2.06 ksi. This is the maximum shearing stress developed in this beam, which is less than tau allowable, because tau allowable is 12 ksi. So it means that the selected beam, the selected W12 by 22 wide flange beam is okay. So this was all about this problem. I hope you have enjoyed this video. Again, if you have any question, you can ask me in comment section. Those who are new to my channel, then subscribe it and keep watching. Also press the bell icon so that you may get the updates about my latest videos. Thank you for watching.